100%. Think about that for a second. That is a number you almost never see in AI benchmark testing. And in something as unbelievably complex and unforgiving as hardware engineering, it's literally unheard of. But a brand new hardware design framework from NVIDIA Research just hit exactly that, a 100% completion rate across all evaluated hardware benchmark suites. It is an absolutely unprecedented benchmark conquest. But here's the wild part. Immediately after dropping this massive bombshell of a number in their paper, the researchers just state plainly, quote, agentic hardware design is not solved. Now, why on earth would they issue such a stark admission right after achieving a perfect score? What is actually hiding beneath that 100%? Welcome to The Explainer. I am absolutely pumped to walk you through today's topic. We are diving deep into NVIDIA Horizon, which is a hands-free agent framework that completely shifts how we approach automated hardware design. You see, instead of treating code generation like a simple question and answer prompt, Horizon actually treats hardware design as a continuous, repository-level code evolution. Okay, let's dive into this. Here is how we're going to break it all down. First, the 100% RTL breakthrough. 2, why hardware is different. 3, the Git-based agent loop. 4, unpacking the benchmark conquest. And finally, 5, token economics and limits. Are at Section 1, the 100% RTL breakthrough, shattering industry benchmarks. Now, as most of you know, working at the register transfer level, or RTL, leaves literally zero room for error. We aren't just writing plausible software scripts here. We're modeling precise, synchronous digital circuits. This highly rigid, totally unforgiving environment is exactly what Horizon is tasked with navigating. And just take a second to appreciate the sheer scale of this success. Horizon, operating in a single-agent, hands-free mode and powered by a fixed GPT 5.3 backbone, hit a perfect 100% pass rate across every single evaluated suite. We're talking ChipBench, RTLM 2.0, Verilog eval, and 9 separate CVDP task categories. Without a single human intervention during the process, it completely swept the board. And what's really fascinating? The one single miss in their entire run was actually due to a defect in the benchmark specification itself, not a failure of the AI agent. Moving on to Section 2, why hardware is different. Plausible code isn't enough. So here's the crucial thing. When you're dealing with actual hardware, writing code that just looks plausible isn't going to cut it. Single-turn code generation, where you give a chatbot a prompt and it spits out a script, well, that might work for basic software tasks. But hardware? Hardware requires exact cycle-level behavior, correct reset conventions, and super strict bit widths. It relies heavily on constant simulator feedback. Single-shot prompts just fail because they cannot iterate against these rigid constraints. Horizon's approach completely abandons that single-turn model in favor of continuous repository-level evolution. It all kicks off with this highly structured markdown harness. Instead of some open-ended text prompt, Horizon requires just 4 structured components. You've got a goal, domain knowledge directions, an evaluator specification, and an acceptance predicate. A Bootstrap agent takes this markdown file and literally compiles it into a full self-contained project pack. From here on out, human hands leave the keyboard, and the system takes total 100% control. Which brings us to Section 3. The Git-based agent loop, or as I like to call it, the tireless automated worker. Let's peek under the hood at the actual engine running here. First, the agent reads the current state and plans a target edit. Then it modifies the files in the work tree and invokes its domain tools. Next, it runs the executable evaluator, so it's compiling, simulating, and checking coverage. All this evidence hits the correctness gate. If it passes, boom, it commits the version. If it fails, it logs the rejection and just immediately tries again. Now, this loop relies on a seriously clever engineering choice. The researchers point out that, quote, problems are defined over Git work trees, not over a fixed repository type. Git isn't just basic bookkeeping here, it's the actual underlying substrate. By relying on native Git commands like diff to see changes and commit to define checkpoints, Horizon creates this cheap and highly effective experience buffer. It perfectly separates the positive fixes from the negative logged attempts, which allows the agent to learn directly from the repository's own history. And this brilliantly illustrates exactly where Horizon sits in the lineage of AI self-evolution. We've seen systems like Alpha Evolve for scientific algorithmic kernels, Satlution for solvers, and ABC Evo for EDA software. But Horizon takes this framework and specifically targets hardware artifacts, like RTL sources and test benches, demanding strict compile and simulate checks before ever admitting a candidate change into the final design. All right, Section 4, Unpacking the Benchmark Conquest, Beyond Iteration Zero. Because let's be real, this was absolutely not a magical one-and-done victory, 47.8%. That is Horizon's aggregate first iteration pass rate across these suites. At iteration 0, which is the repository state after just the very first agent attempt, less than half of the tasks actually passed. The real magic of Horizon is that it relies entirely on its automated debugging iterations to bridge that massive gap between 47.8% and 100%. And the variance in how hard these tasks are, it's absolutely massive. For a suite like RTLM 2.0, the system achieved that perfect pass rate in just 2 iterations. For debugging tasks in CID 016, it took 13 automated iterations. But for RTL code completion under CID 002, the agent required a grueling 82 automated attempts before it successfully passed the gate. It essentially just grinds away, hypothesizing and testing over and over until the simulator finally turns green. Which brings us to Section 5, Token Economics and Limits, the friction of the system. First off, we really need to understand exactly where all this computational horsepower is going. Horizon is essentially performing the heavy workload of a daily hardware engineer. It's completing failing code, it's implementing modules from written specs, adapting existing RTL, linting, generating test stimulus and checkers, and localizing functional bugs. It is doing very real, very rigorous engineering legwork. But man, the cost of doing all that legwork is staggering, 56 million. That's the number of tokens chewed up by just the CID 002 code completion category alone. Across all 9 CBDP categories, the system burned through over 200 million tokens. Hitting 100% by brute forcing 82 iterations creates immense economic friction that we just can't ignore. Now, what's really interesting here is how they kept this from completely bankrupting the project. Notice the massive disparity in the token breakdown. Because Horizon holds a persistent model session across all these iterations, 91% of the total tokens are actually treated as cached input. That means the harness, the project pack, and the stable source code aren't being billed over and over. Only 9% of the tokens are newly billed, and those are mostly just the new code diffs and evaluator outputs. That caching efficiency right there is exactly what makes the whole system economically viable. Still, we've got to ground this explainer in reality. There are some very real, critical system limitations here. Because the agent's only goal is to pass the acceptance predicate, there is a very high risk of reward hacking. A pass might just mean the AI perfectly hacked the visible harness without actually fulfilling the true underlying design spec. Furthermore, these benchmarks, they're just controlled proxies. Real hardware involves long PPA turnaround times, power, performance, and area, which can take days to evaluate, not seconds. Oh, and the quality of results for the actual hardware synthesis was not even optimized here. Which brings us right back to square one and that stark admission from the NVIDIA team that hardware design is definitely not solved. Horizon is undoubtedly a phenomenal leap forward in automated engineering. It absolutely proves that iterative, Git-based evolution beats single-turn prompting every single time. But as we look at those massive iteration counts and the ever-present risk of reward hacking, I want to leave you with a provocative question to chew on. Is Horizon actually designing perfect hardware, or has it just learned to perfectly play the benchmark game?